So, shall we take a new example?
Sure. Are we going to do something different from what we did last time?
Maybe superposition or
Okay,
Thevenin
let's
or-
try. Actually, I think we gave them the superposition as a homework last time.
Correct.
We'll take some other circuit and do superposition
Yeah,
this time.
yeah.
Good idea. Good
Yeah.
idea. Let's do it.
So, I have a current source going upward.
Going upwards. Okay.
It's actually given in time domain.
Oh.
5 cos 3t.
Okay. 5 cos 3t. Okay.
And then a 0.2 farad capacitor is connected in parallel.
Okay. So now
One more
we have
step.
extra one more step of calculating the
Reactance.
reactance and so on. Okay. So what is the value of the capacitance?
0.2 farad.
0.2 farad. Okay.
Large capacitor.
Large capacitance.
Then, yeah, from the top of the 0.2 farad, 10 ohm resistor. in
10 ohm
series.
resistor in series. Okay.
So from the end of the 10 ohm, there is a capacitor coming down.
Okay.
Yeah. And the capacitor value is 0.5 farad.
0.5 farad.
And then there is a current source parallel to 0.5 farad.
Going downwards or
Going
upwards?
downwards.
Going downwards. Okay.
2 cos 3t.
2 cos 3t. Okay.
Yeah. Both in amperes.
Both in amperes. Okay. So
And I wanted to find out the power dissipated in the 100 ohm resistor.
Power dissipated in the 10 ohm, right?
Sorry, 10 ohm resistor.
10 ohm resistor.
Yeah.
Okay. So you want the power in the 10 ohm resistor. Okay.
Anyway, there is no power dissipated in the other elements.
Correct.
So the power dissipated in the circuit is also same.
The circuit is also the same. Correct. Okay. And you wanted to solve it using superposition.
Because there are two sources, I thought that that may be a...
Correct. That's true. But you know, last term we saw in DC circuits, we saw that you cannot use superposition for calculating power in DC circuits. I'm guessing the same thing also is valid for AC circuits, no? I'll just say this current I. I'll call this some unknown current I.
Yeah.
Right? Okay. And you want to use superposition.
And the sources we will represent now in polar or rectangular.
Correct. Maybe we'll do, we did rectangular for some previous problems. Let's do polar form this time.
Okay.
Okay.
Yeah.
So let's do one thing. Actually, in this case, because you only have a capacitance real part, it may be easier to just use rectangular. We'll just do that.
Yeah.
We'll just do that. So, and you want to do it using superposition. Okay.
So first we'll write the reactance, etc. in.
Correct. We'll first thing to do is redraw it with in complex currents, voltages, impedances, right? Okay, let's do that. So we'll just, or what is easier is maybe I'll just write it in a different color.
Yeah.
That is good enough for us, no?
Correct.
5 cos 3t. So first of all, we know the omega from this.
Yeah.
Right? Omega is basically 3. Right? That's what we know.
Yeah.
Omega is 3 radians per second. Then, so that is, in case we need it at any time. But the phasor notation for cosine was plus j. It was leading the sign by 90 degrees. So this will be plus j5 amperes.
Okay.
Is that correct?
We take the peak or RMS?
We take the RMS. Okay, good point. So then 5 by root 2.
Root 2.
Okay, good catch. So 5 by root 2.
We can use the peak also.
That's right.
Throughout, if you follow.
Actually, you'll have trouble when you find out the power.
Correct.
Right?
Yeah.
So you have to, even if you follow the peak, at the end, you'll have to be careful when you find out the power.
Yeah.
We'll just use the standard notation.
Yeah.
Plus j 5 by root 2.
Yeah.
Right? That is this phasor. This phasor is plus j2 by root 2.
Yeah.
So which is just j root 2 amperes. And now we need to find out this omega we need for finding out the complex reactance and complex impedance
Correct.
in ohms.
1 by j omega c.
Yes, so 1 by j omega c. So this is basically 1 by
0.6.
3 into 0.2, 0.6. So 1 by 0.6, right?
Yeah.
So 5 by 3.
Yeah.
So we'll write it like this in ohms, right?
Yeah.
Minus j 5 by 3 ohms.
Yeah.
Is this correct? So 3 omega c is 3 times 0.2. That is the reactance, which is 0.6. 0.6 is basically 3 by 5, right? And minus j over omega c is the impedance,
yeah,
in ohms. So minus j into 5 by 3. Now this one now will be in the same way. 3 into 0.5 is 1.5. So 1.5 is basically 3 by 2. So this would be minus j 2 by 3 ohms.
Yeah.
Correct?
Yeah.
Okay. And this is 10 ohms. So I think we have everything in place. You wanted to use superposition.
Yes.
Okay. Let's just check once more to confirm all the values are right. So 2 cos omega t, cos is a j, will give you a j. Peak value is 2, so RMS value is root 2. Here 5 cos 3t, same way it's j 5 by root 2 amperes. The omega c is 3 times 0.2, 0.6. So 1 by j omega c or minus j by omega c, and minus j by 0.6, which is minus j into 5 by 3. 5 by 3 is 0.6. This would be 0.5 into 3, 1.5, minus j over 1.5, right? So which is minus j into 2/3. So I think we are good.
Yes.
So let us say we are now use superposition. So I am going to say
due to j 5 by root 2.
yes. So we are going to consider only this. So current sources are open circuited, so that is straightforward. And so now our circuit is relatively simple, I think. So minus j.
Can we use source transformation here?
Ah, okay. Of course you can. You can actually transform this source, no? Let's do that. Maybe we'll do that.
That's okay only.
That's okay. I think we can perfectly do that. In fact, a lot of cases it's easy to simplify it. Here I thought you only have 2 branches. This is Z1. We are anyway open circuited.
Current division.
Current division problem. So you can. By the way, source transformation will absolutely work.
Yeah.
Right.
Yeah.
So what I have noticed is that if the circuit is somewhat simple, just calculating, using impedance, so current splitting through 2 impedance, things like that is faster.
Yeah.
But if you have even 3 impedances, source transformation is very useful. Very useful. So this time, shall we just do using current splitting, current division?
Current division.
Okay. And this is 10 ohms.
Yeah.
And this is I1, I'll call it, because this is the current due to this first current that we are calculating. So I1, and we have seen normally it will be the total current. So J 5 by root 2 into the impedance in the other arm, opposite arm, right? So minus J 5 by 3 by the sum of the impedances. Yeah. So minus J 5 by 3 and minus J 2 by 3.
Plus 10.
Plus 10, of course, in the denominator.
Yeah.
Okay. So this would be, we need the calculator for this, I think. So let me, let's see if I can, I think it's, shall we simplify it algebraically? Then we can do the division of the number. Maybe we can do it that way. Because this is easy, exactly. So 3's we can cut, minus j squared is plus 1, right? So 5 5 is 25 by root 2 will be the numerator.
Yeah.
And denominator will be 10 minus j7. Oh, sorry, 30 minus j7.
Yeah.
30 minus j7. Yeah. Maybe we can just do this. Maybe you can leave the root 2 away aside.
We can retake
We can
it.
retake it later. So you
Yeah.
just find out 25 by 30 minus J7.
So this is some fraction.
Okay, then now you can just divide it by root 2
Also.
and then get the decimal numbers.
Yeah.
It may be easier if it's such a
Yeah.
large fraction.
Yeah. So it's 0.558.
Okay, so maybe I'll just call it 0.56. We'll cut it, round it to 2 decimal places.
Yeah. J 0.13.
Plus J, no?
Yeah.
Amperes.
Yeah.
Okay, so we have the current I1. So the current through 10 ohms only due to 5 cos 3t.
Correct.
Okay, now next we will do the current due to just due to this 2 cos 3t.
Yeah.
So again this 5 cos 3t will get open circuited. So we'll have this network. So maybe we can just do this. Downwards current J root 2 amperes. Correct. J root 2 amperes.
Yeah.
And downwards, right?
Yeah.
I just wanted to check
Yeah.
that. Okay,
Yeah.
good. And there will be a capacitor across it. And that was minus J 2/3 ohms.
Yeah.
And then we had the 10 ohm resistor.
Yes. And another capacitor there.
And another capacitor. And the other things minus J 5/3. Okay. And this current is I2. Well, let's just use the same direction. You can just add I1 plus I2. And actually it works out because this current is downwards.
Yeah.
Right. So, okay. We want to find out I2.
Once again current division.
Once again current division. So, it is the total current times the current in the other, the impedance in the other arm.
Yeah.
Which is minus J2/3 by the sum of everything.
Yeah.
2/3 minus J5/3 plus 10.
Yes.
Okay. So, this will be I think 2 root 2 by 30 minus J7.
Okay, this is 60 root 2
Okay.
minus 14
14
root 2.
minus J14 root
Yeah.
2.
Yeah.
Okay.
You want fraction?
No, this is okay. Let's get it in decimals, I think.
Yeah.
So 84.85.
Yeah. We'll try
So,
that.
okay, got it. So 84.85 and this is correct now, 30 minus J7.
Yeah.
Because I'm just thinking because we had a 25
Hmm.
in the numerator divided by this, that only gave me 0.56.
Now this is huge current.
Yeah, this is a huge current. I'm just
So-
wondering whether we have written it correctly.
So I think I made some mistake.
Okay. So it should be 2 root 2.
Yeah. So
We'll just do 2 by.
wait, there's a mistake.
Okay.
So 2 into 2 divided by yeah, you are right.
Oh, okay. It is
Let's
smaller.
Let's
Okay.
erase this.
Okay. I got a little bit worried because the
Yeah.
denominator is the same.
Correct.
This is also smaller.
Correct.
Okay.
It's 0.089
0.089
plus J 0.02.
Okay. So amperes.
Yeah.
Yeah, because this current is also 2
Less-
cos 3t
Yeah,
smaller,
okay.
so I was a little bit worried. Okay,
Yeah.
excellent. So now we know the total current I is
You
simply
know what's
I1
the
plus.
mistake I did?
Oh, what was it?
Instead of dividing, I multiplied.
Oh, you
2 root.
multiply. Oh, I see. Okay. Okay, so it's just I1 plus I2.
Yeah.
So 0.56 plus 0.089
So if the other one you can say
0.56.
0.56.
No, we can just add the individual real and imaginary parts. Okay.
0.649.
0.649. I just write as 0.65.
Yeah. Plus J 0.15.
0.15 amperes. Perfect. Right?
Is it matching? 0.02 here and
0.02 is 0.13. So it's 0.15.
Yeah.
Perfect.
Yeah.
So this is in real plus imaginary. To find out your question was find out the power. So we need to find out the magnitude of this current, right? Of this current, which is the RMS value of the current.
Yeah.
So magnitude of the current should be root of 0.65 squared plus 0.15 squared.
Yeah.
Or I think we can just do it independently, but 0.65 squared plus 0.15 squared.
Root of that.
Yes, root of that.
That's 0.651.
0.651 because the other is too small. So 0.65.
Yeah.
I'll leave it as 0.651 amperes.
0.651.
Yeah. So we'll just do it like this. Okay. So we'll write it like this.
So I squared.
I squared times 10.
Yeah.
So power times 10 ohms.
0.425. So that's 4.25 watts.
4.25 watts?
Yeah.
Oh, this is 0.425.
Yeah.
Oh, into 10. Oh, perfect. Okay, great. Okay, so looks like this is the power dissipated in the 10 ohm resistor.
Yes.
In fact, you can see clearly that if you had just used this squared times 10 plus this squared times 10, it would never have given you 4.25 watts. The sum of these two would have been much smaller, right? Okay. I think we would have, so good. So you have to find out the current through the 10 ohm using superposition, then take the square root. I mean, take the RMS power, the squared times R. Perfect.
So we should always cross check. No?
We should always cross check. Correct.
So what we will do? We'll consider 10 ohm as some load and then make a Thevenin equivalent of the circuit.
Oh, okay. Oh, Thevenin equivalent of the rest of the circuit. Okay, so let me understand. I'm going to make a copy. So now that you are coming up with newer ways of solving the problem, will move to another page and let me understand what we want to do. I'll leave these numbers in here. So
I'll consider 10 ohm as the load resistance.
Okay.
And the rest of the circuit, I want a Thevenin equivalent.
Oh, I see. So you want to build a Thevenin equivalent for this portion.
Correct.
Right?
Exactly.
So this will be some Thevenin, right? Not Norton. Doesn't matter. So let's say Thevenin. All right.
So is Norton going to be easier?
I think it is about the same. No, I think it is the same.
Yeah.
I don't think it will be easier.
Yeah.
So I just saw the current source.
That's true.
And I thought suddenly, you can actually use source transformation to solve this.
Yeah.
Right? That's what you pointed out right at the beginning.
Correct.
Right? But let's do the Thevenin.
Yeah.
Right? So we'll do this VTH and ZTH for this portion.
Yes.
Across A and B, no?
Yeah.
That's what we want. Okay, let's do it. Remind me again, Bobby, how do you find out the Thevenin equivalent? Was it we used some technique to find out the open circuit voltage?
Yeah, this open circuit voltage and then the impedance seen from
total impedance seen across those two nodes.
Yes.
Okay, let's do that.
Yeah. So just for clarity, maybe we can open circuit that.
We'll remove the 10 ohms.
Yeah.
Right?
Yeah.
So, okay. So what I will do, we will go to the next page. We will paste the same network but remove the 10 ohm.
Yeah.
Remove the 10 ohm. So across these two nodes we want to find out across A and B.
Yes.
We want to find out the Thevenin
So
equivalent.
we can find out voltage at A, voltage at B, and then find out the
Correct.
difference in voltage.
You are right, because these two networks are independent. There is no current through this wire.
Correct.
Right? Because KCL, there is one loop here, there is no third loop.
Yeah.
Okay, let's just do that. So the voltage at A, VA, is going to, once you remove that open circuit, that 10 ohm, no?
Yeah.
Remove that 10 ohm.
So the current multiplied by
Impedance.
Yeah.
So it will just be J
by
5 by root 2 into minus J 5 by 3. So this would be minus J squared, which is plus 1, 25 by 3 root 2.
Yeah.
Volts. Correct?
That's
No.
true.
So
the J term is gone.
J term is gone. And VB is, VB is negative now. So because current is flowing like this,
Yeah.
VB is negative with respect to the bottom node.
Yeah.
So this will be your reference now. With respect to reference, A is,
Yes, yes.
right?
In fact, maybe we can mark that plus minus for
We'll show like this, VAB.
Yeah.
Okay. So now VB is minus J root 2 into minus J 2 by 3. So J root 2 into minus J 2 by 3 is this voltage, but it is a drop because the current is flowing like this, right? So B will be in that negative sign.
Yeah.
So minus J into minus J is minus 1. So minus 2 root 2 by 3. That's correct?
Yeah.
2 by 3. Now VA minus VB would just be, well, sum of these two.
Yeah.
So this is basically minus 4 by 3 root 2.
Yeah.
Right? So minus 4 by 3 root 2.
Correct.
So this would just be 29 by 3 root 2.
Yeah.
This is your
Because it
VThevenin.
is VA minus VB.
VA minus VB. So it will be 29 by 3 root 2. This is your VThevenin in volts.
Yeah.
And then your Zthevenin.
Yes.
Well, for finding out Zthevenin, we have to short circuit all voltage sources, open circuit all current sources, and then find out the impedance, effective impedance.
Correct.
Okay. Oh, here it's easy.
Yes.
We just remove the two current sources. Then across A and B, it is just a series of these two.
Correct.
Right. So we can write Zthevenin is just sum of these two. So minus J into 7 by 3.
We will draw just for clarity.
Just for clarity, shall we draw it?
Yeah.
Okay. So this is A. So the two current sources have been open circuited.
Yes.
So this is my minus J 5 by 3 and this is minus J 2 by 3. So minus J 7 by 3. Okay.
Nice.
Nice. So now we have VThevenin, Zthevenin.
We'll
So
put the 10 ohm.
we'll put the 10 ohm back,
Yeah.
right? So now we can, so this is A and B, and we had taken A as positive, no?
Yeah.
Reference. So
Yeah.
29 by 3 root 2.
Yeah.
So 29 by 3 root 2 volts, and this was minus J 7 by 3 ohms. And across that we connected 10 ohm. Okay, and from A to B we have a current now.
Yes.
This is the current I. So we wanted to find I and eventually power, no?
Correct. Correct.
And once we find I, if it is the same,
Then we are.
we can assume. Okay, so this is simply 29 by 3 root 2 by 10 minus
J7 by 3.
J7 by 3. We'll quickly simplify it and then use the calculator.
Yeah.
So let us say I am going to multiply it. We'll keep 29 by root 2 here. We'll multiply by 3.
Yeah.
Okay, so 29 by root 2 by 30 minus J7.
J7.
Oh, 30 minus J7 we are getting again.
It was there.
It was there.
What about the numerator?
We'll see. 30 minus J7 was there.
But
Numerator was 2 root 2 and something else.
25
Alright.
by root 2.
25 by root 2. We had 2 root 2 here, right?
Yeah.
So this is 4 by root 2.
Yeah.
So 29 by root 2.
Okay.
Correct, no?
Yeah.
I think it should give us a, yeah. So
Yeah.
29 by root 2 is correct.
Yeah.
So I think it is giving us the same answer.
Should we check what the calculator gives?
Sure. We'll let's check. So we'll write it in rectangular form.
Yeah.
So that we are sure that.
29 by root 2 divided by 30 minus
7j.
yeah 0.64.
Yeah, 0.649 or something,
Yeah.
right? So 0.65. I think plus j
0.15.
0.15. Correct. That's what we got.
So
Perfect.
the current is same.
Current is the same.
Of course,
And
the
power will be the same. You just find out the RMS value of this and correct.
great. So
So we have proved that Thevenin equivalent works for numerically,
yeah.
right?
And it's matching.
And it is matching when we did it
Chance
using
of doing
superposition.
the same mistake twice is low in this one.
That's right. That's right.
Yeah.
And looks like you also, I think, pointed out, no, you can do source transformation for each one and also do it.
Yeah.
There are always many different ways. Once you know,
Correct.
right, you can convert this portion to Thevenin, this portion to Thevenin, then you will just get one single mesh. So then you can also do it that way. Maybe students can try it out as a homework.
Correct.